Hello again. After finishing that last video, I thought, man, that leads really nicely into another video, and this is that video. So, I'd like to talk now specifically about the semantics of an expression tree. So, what is the meaning of an expression tree? And like the other questions, what is the meaning of this or that, this is going to have a lot of different answers that are all correct. So again, a simple example of an expression tree is what we get if we read in something like 3 plus 4 times 5 into a computer. We'll get an expression tree that looks something like this. There's a plus node with a 3, and then a times node with a 4 and a 5. So what does this mean? There are lots of different things you can imagine it means. One is instructions to calculate the value of this. It's the instructions to compute a number. For instance, in this case, you start with the expression tree itself, and to compute the number, you kind of go bottom up, because that's the only way you can go. So you say, okay, we have a plus node and it has a 3, which is already a number, and then on the other side we have the product of things. So that becomes a plus node with the 3 just still sitting there, and then the 4 times 5 is evaluated to 20. And then we have two numbers that we can add, and we get 23. So you can treat this thing as instructions to calculate a number by going bottom up. Another thing that an expression tree can be is instructions to display the expression. So this is another meaning that an expression tree can have. If you have something like, again, 3 plus 4 times 5, let's say you want to show this on screen, and you want to display it using some pretty LaTeX. You can start evaluating this not into a number, but into a LaTeX string. So you might get something like 3 plus the string for backslash c dot, which is LaTeX for times 5, and then evaluate this. This will become 3 plus 4 c dot 5. So that's another thing that you can do with an expression tree. You can also, instead of evaluating an expression tree directly like this into a number, like I mentioned in the previous video, you can either run code or you can compile it. In the same way, you can either evaluate an expression tree or you can treat it as instructions to generate some code. So like, let's say you have some formula that you're using for some operation on a data set. Like, let's say in some context you have some definition that goes like SXY is some function of a vector X, a vector Y, and a vector sigma, where these are vectors of lots and lots of data points, and this is defined as the sum over all elements of the vectors of xi times yi divided by sigma I squared. This may be useful in a linear regression, say. I meant to put the bullet point down here. Instructions to generate code. To calculate something. So then this would become maybe some C code, like double S, X, Y, just copying down the name of int n number of elements in the vectors, double star X. So a pointer to some doubles, and same thing, Y sigma. I need to use actual English characters since this is C code, and then it might have a for loop in it. And the summation here would become a for loop when you generate code. Int I equals 0, I less than n, I plus plus. So start iterating through these things, etc. And then there's some more code that just calculates this. So that's another thing you can do with an expression tree. And you could imagine, this is C code, but you could imagine generating code for a GPU or something. So just about, any kind of hardware that you could use to evaluate some math, you can generate code from an expression tree. And then another thing you can do with expression trees, which I mentioned in the last video too, is you can pattern match with them and rewrite other expressions. So you can treat an expression tree, if it's suitable, as a way to rewrite other expressions. And I will give some examples of that real quick, since that's really important for doing computer algebra and sort of optimizing things. One thing that I'll start off with is I gave some examples of expression trees already. Like one thing you can do is say 3 plus 4, and that will have an expression tree. There will be a plus node with a 3 and a 4 hanging off of it. And you can also, you can imagine writing like f of x, like some kind of function, as the expression tree that has an f that's applied to an x. And I'll just mention that just as a non-example, you can nest expression trees however you want. Like you can say 3 plus 4 applied to x, as if 3 plus 4 is a function. This doesn't make sense, but you can imagine making an expression tree like that, where you have plus 3, 4, all as a node that's applied to an x. And so this is a non-example, because it doesn't mean anything. But the idea of putting expression trees inside of other expression trees is important, and so I'm writing this to illustrate that. So more examples of ways that you can pattern match and rewrite expressions with expression trees. I'll give 2 more examples. One is I'll write a rule I'll just call it swap. And it's going to take, as an example, x plus y will become y plus x. So it'll swap 2 elements of something, some operation. And that can be written, say, in text form. It can be written as something like f such that f is associative, which means that it's legal to swap its arguments. Applied to 2 arguments, x and y, goes to f of y, x. And that might be written as the expression tree. First of all, we've got this operation. It's f, it's this whole thing applied to x and y. And this whole thing has this operation as the root part of it. So we've got, and this is pronounced such that. So we've got f, or actually I meant to put in such that associative of f. So associative is a function that I'm applying to f. So f such that associative f, all of that applied to x and y goes to f applied to y and x. So if we take this rule and try to apply it, okay, and then to use this thing, you need to have some notion of what it means for an operator to be associative, or some way to tell if something's associative or not. So let's say we have a context of a bunch of stuff, a bunch of information and data. So we can say maybe associative plus. Maybe this is just asserted in the context. And maybe associative times. These are both associative, which means you can swap the arguments any which way. So now let's say we are trying to run this swap rule now on 3 plus 4. So we've got the expression tree plus 3, 4. Now, what happens? This big old expression tree right here, this left-hand side of the rule, starts getting matched against the expression we're applying it to. So this top node that I have circled here, all as one big node, gets matched against plus. So it says, okay, I've got a plus, and I'm going to match it against something such that something else. And then such that, this is a special rule, or a special expression. It's not just matched to whatever this thing is that it's being matched against. It has some behavior. So such that when you match it against something, it binds its left-hand side to the thing that you're trying to match. So the first thing that we do is we get f equals plus. And then such that this rule, or this expression, starts looking at the right-hand side and tries to validate that. So it says, okay, I need to validate associative f. And it says, okay, associative f. Well, f is plus, and then it looks through the context, because that's what it does, and it says, oh, we have associative plus, so that's good. Check. And then this thing is done. And then it's able to proceed and match x and y. And it binds x equals 3 and y equals 4. And then it's done binding the left-hand side. Then it's able to go look at this. The swap rule is starts binding, or substituting its bindings into the right-hand side. So f again is plus, and then we get y and x, so 4 and 3. So then we get 4 plus 3. So there's an example of using something that sort of looks up some data by using a rule that when it's bound, it goes and does something. And then I'll give one more example. I will show, let's say we want to delete the group identity from something. Like, for instance, let's say we have x plus 0, and we want to take that to x. Or x times 1, and we want to take that to x. So, because 0 is... it is anything plus 0 is itself. So this is going to be called identity elim, and it will eliminate the group identity. So what this is going to look like is kind of using the same syntax as this up here. It's going to be some function f such that it's got a group identity, and then applied to something and its group identity. So what that's going to look like is f such that group identity such that group identity of f evaluates to z applied to x and z. That evaluates to x. And that, okay, so then the way that this expression tree looks is, again, we have something applied to some things, and so that something that's applied to some things is this part over here. And at the highest level, it's a sort of such that operation. So we've got something such that something else. So we've got f such that group identity of f evaluates to z. And now this part over here, group identity of f evaluates to z, this is saying something evaluates to something else. So I will put this arrow here. This says, or this is pronounced evaluates to. And then this is applied to group identity which itself is applied to f, and then evaluates to is applied to z. So we've got all of this. This is the function here, or the operation, and then the arguments that it's applied to are x and z. Then this thing evaluates to x. And okay, then for an example of this, let's show some examples. So again, in order for group identity to be meaningful, we need to have some notion of whether something has a group identity, so we can start putting that into our context as well. So let's say in our context, we also have group identity of plus evaluates to 0 as a fact in our context. And group identity of times is 1. So then when we evaluate group identity, or identity elim, the name of this rule, on, say, let's say x plus, I'll use a different letter, a plus 0. Then, okay, so a plus 0 has the expression tree plus with an a on the left-hand side and a 0 on the right-hand side. And then when we execute this rule, we start pattern matching. The expression tree has a plus node at the top, and so we bind this big old thing to the plus node. Now, this thing, we start with a such that expression, and then the such that has an f on the left-hand side, so we just bind f equals plus. And then we need to evaluate the right-hand side and show that this holds. So then the right-hand side is an evaluates to expression, and this also has its own little special behavior. It takes the left-hand side and it substitutes whatever you already have into the left-hand side. So we get group identity of f, where f is plus. Make that a better plus. And then it looks in the context and says, okay, we're trying to evaluate something. So what does group identity of plus evaluate to? Looks in the context and says, oh, group identity of plus evaluates to 0. So then it's able to say, okay, so then z is 0. So we get z equals 0. And then we have finished evaluating this whole thing. So we get check mark, yeah, it's good. And then, so that's good. So then we're able to start recursively binding the rest of this tree. So we say, okay, x, that has to be bound to a. So x gets bound to a, and then we have z over here, and that has to be bound to 0. And z is already bound to 0, so that's good. So there's no new bindings, we just get a check mark. And if this was something other than 0, like 10, then we would get an error. Then it would say, oh, z is 0, it can't also be 10. So, but in this case, in this example, Z is already bound to 0, and it's getting bound to 0 again, so that's good. Okay, so then, once we've done all that, we've bound the whole left-hand side, and then we just substitute our bindings into the right-hand side, which is X, which is bound to A, so we get A. So identity elim of A plus 0 is just A. So that's another example of how you can use a expression that has some special behavior, some code that runs that does something, that checks whether something can be bound and gets information. Like here we get the group identity, get some information about the operation so that you can tell if you can run the rule on this. So there's some more examples of expression trees and how they can be used, how they can, like what sorts of meanings they can have. Let's see. I guess I'll see you next time.